So we now know how to graph inequalities in two variables. Let's talk about solving systems of inequalities. If two or more inequalities in two variables are related, you are dealing with a system of inequalities. The solution to a system of inequalities in two variables is the region of the graph that satisfies each of the inequalities of the system. Again, shading is used to show the region. So your solution set will be a shaded region that satisfies all of the inequalities in the system. Here are steps for solving systems of inequalities. Step number 1. Replace the inequality sign with an equal sign in each inequality and sketch the graphs of the resulting equations on the same coordinate plane. Use a dashed line for less than or greater than, and a solid line for less than or equal to or greater than or equal to. Next, choose a test point to determine the region that would be shaded for each individual inequality. Do not shade yet. I like to use little arrows along each curve to tell myself what direction I want to shade. 3. Determine where the shading of each individual inequality would overlap. Shade this region to mark the solution. So your solution to the system is going to be where all of the shading would overlap. That's the region that you want to shade. 4, locate the vertices. Vertices are the corners of the solution set by solving the appropriate systems of equations. So if you're trying to find the corners of a solution set, those are going to be the intersection of your curves. And as you guys already know, intersections of curves, we can find the intersection points by solving the system of equations for those two curves. Let's look at an example here. Sketch the graph and label the vertices of the solution set of the following system of inequalities. We have x minus 2 is greater than negative 6, and 5x minus 3y is less than negative 9. We begin by sketching the line x minus 2y is equal to negative 6, right? We swap our inequality symbol for an equal symbol, and we sketch the graph. Well, here we have a line that is written in standard form, ax plus by equals c. Again, I always think it's easiest to plot the intercepts here, and then we can sketch the line afterwards. So plug in 0 for x. Plugging in 0 for x will give us our y-intercept. 0 is equal to negative 2y, which is 0 minus 2y is equal to negative 6, sorry. Dividing both sides by negative 2y gives me y is equal to 3. We have a y-intercept here at 0, 3. Plugging in 0 for y now will give me the x-intercept. This tells me x is equal to negative 6. I can plot my x-intercept at negative 6 and connect the dots. I'm going to use a dashed line because our inequality has no equal to part to it, right? It's just greater than. Next, sketch the line 5x minus 3y is equal to negative 9. That's our next inequality that we're going to sketch. Again, we have a line that's written in standard form. Easiest to plot the intercepts. If I plug in 0 for x, that will give me the y-intercept. Here we get y is equal to 3. That's convenient. It's actually the same y-intercept. And plugging in 0 for y will give us our x-intercept. 5x is equal to negative 9 now, which means x is equal to negative 9/5. Just slightly greater than negative 2 here. Okay, so we have our intercepts. We can now connect the dots with a dashed line. Again, we're using a dashed line because there is no equal to component of the inequality. Next, choose a test point to plug into each of the original inequalities. And you can pick any point on the graph that's not on the line. The easiest test point is going to be the origin 0, 0. We can easily plug that into each of the original inequalities. So we plug it into the first one. That gives me 0 minus 2 times 0 is greater than negative 6. 0 is greater than negative 6. That is a true statement. So for our red inequality, we want to shade the region that includes the origin. So what do? Rather than shading it and creating a big mess right now, I just put some arrows along the curve to tell myself what direction to shade. Next, we plug our test point into the second inequality. 5 times 0 minus 3 times 0 is less than -9. This gives us a false statement. 0 is not less than -9. Because 0 is not less than -9, this test point gives us a false statement. We want to shade the other direction. In other words, up to the left for our blue line. Now, the solution set to the system of inequalities is where our shading overlaps. And where does the shading overlap? Well, that's going to be this region right in here. The shading from both lines intersects there. All right, there is the region of our solution set. Finally, to determine the vertices, we solve the system of equations. Now, again, vertices are just corners of your solution set, and there is only one corner of the solution set. And based off of our graph, we know it's actually the y-intercept at 0, 3. So we have the solution just based off of the graph, but we're going to go through and prove that it's 0, 3 by solving the system of equations, right? Again, the intersection of two curves is the solution to the system of equations. So I just replaced each of our inequality symbols with an equation, and now we can begin to solve this system. I would probably solve this system using substitution. We can easily isolate the variable x. X is equal to 2y minus 6. I can substitute that into my second equation. 5 times 2y minus 6 minus 3y is equal to -9. When we distribute in, we get 10y minus 30 minus 3y equals -9. 10y minus 3y, well, that's going to give me 7y. And if I add 30 to both sides, I get 7y is equal to 21, which gives me y is equal to 3. And if y is equal to 3, I can back substitute it into my equation here to solve for x. X equals 2 times 3 minus 6, which does indeed give us x equals 0. Okay, and so we just verified there algebraically that the vertice, or the corner of our solution set here, is indeed at 0, 3. Let's try one more. Sketch the graph and label the vertices of the solution set of the following system of inequalities. Now we have 4 inequalities here to worry about. We have y is greater than x squared minus 4, y is less than or equal to 2x plus 3, x is greater than or equal to -1, and y is greater than or equal to 0. Again, we begin by sketching a graph of each of these equations. We replace the inequality with an equation symbol. The first one would be y equals x squared minus 4. Well, this is going to be a parabola. Notice our parent function would be y equals x squared, and the minus 4 here shifts our graph down 4 units. That means my vertex is going to be here at 0, -4, and we could find the x-intercepts by factoring and finding the zeros. That's going to be plus or minus 2. There is my parabola. And notice that when I draw in this parabola, I am going to use a dashed line because the inequality does not have an equal to component. Next, we want to graph the line y equals 2x plus 3. Well, this line is written, in slope-intercept form. We know that we have a y-intercept of +3, and we know that this graph has to have a slope of 2. That means we go up 2 over 1, up 2 over 1. And when we draw out this line, we're going to use a solid line because we have the equal to part of our graph. Next, we graph the line x is equal to -1. X equals -1. Well, that's the equation of a vertical line. Where are all the x coordinates -1? That would be this vertical line right along here. So we're going to draw in our vertical line at x equals -1, and we're going to use a solid line because we have an equal to component again with our inequality. And finally, we want to graph the line y equals 0. Y equals 0 is a horizontal line right here along our x-axis. Again, we're going to use a solid line because we have the equal to component of our solution set. Of our inequality, the equal to component of our inequality. Now we want to choose a test point. Well, for our parabola and for our line, we can easily choose the test point 0, 0, our line with a slope of 2 here. We can easily choose 0, 0. Let's test this in our quadratic inequality. If we plug in 0 for x and 0 for y, we get 0 is greater than 0 squared minus 4. Well, 0 is greater than negative 4. That is a true statement. So for our parabola here, we want to shade the region that includes our test point at the origin. That means we are shading inside of our parabola. We can also use the test point 0, 0 for our line with a slope of 2. Let's plug that into the second inequality. 0 is less than or equal to 2 times 0 plus 3. Well, 2 times 0, that's 0. We get 0 is less than or equal to 3, and that is a true statement as well. So for our blue inequality here, we want to shade, again, the region that includes our test point at 0, 0. We're shading down and to the right from the blue line. Now, our vertical and horizontal components are pretty intuitive, I think, to figure out where to shade. If we want x values that are greater than or equal to negative 1, well, greater than or equal to negative 1 means we're going to take our vertical line at x equals negative 1, and we want to shade to the right. We want x values that are greater than or equal to negative 1. Similarly, with y is greater than or equal to 0, y equals 0 is our horizontal line. We want to shade above that horizontal line. All right, so these are the directions that we want to shade everything. Now we have to figure out where our shading is going to overlap. We want to shade inside of the parabola, below and to the right of this line with a slope of 2, to the right of our line x equals negative 1, and above our horizontal line y equals 0. That gives us this region right in here. So we've shaded in our solution set. Now we want to find the vertices. To find the vertices, we can solve the appropriate systems of equations. Now, a few of these we can find actually just by looking at the graph. We know that one of our vertices, one of the corners of our solution set right here, is going to correspond to our x-intercept, okay, our x-intercept of our parabola, and that's going to be at x equals 2. That would be the ordered pair 2, 0. Over here, we know that this corner is the intersection point of x equals negative 1 and y equals 0. Well, that just means that the corner has to be at negative 1, 0. And similarly, we have our intersection point of our vertical line and our line with a slope of 2, and we can tell based off of the graph that they intersect at negative 1, 1. All right, and so we can plug that one in there as well. The last one, all right, the last corner of our solution set is right up here in the top right. And the intersection point is not as obvious. Based off of the graph, we can't actually tell what it is. So to find this last vertice, let's actually solve out the system of equations. Now, this is the intersection of our line with a slope of 2. Okay, that's this guy right here. And our parabola. So our system of equations is going to be y equals x squared minus 4 and y equals 2x plus 3. Okay, so the best way to solve this system of equations, I think, is going to be substitution. Notice we already have y isolated in the first equation, so we can plug that in for y into the second equation, and that gives us this quadratic. X squared minus 4 equals 2x plus 3. Because we have a quadratic equation, we want to set it equal to 0. If I bring all these terms over to the left, we get x squared minus 2x minus 7 is equal to 0. And to solve quadratics, we want to consider factoring. Now, this quadratic is actually not factorable. So if we end up with a quadratic that is not factorable, our next best bet is going to be using the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In this case, we get x is equal to 2 plus or minus the square root of 4 minus 4 times 1 times negative 7, all divided by 2. Well, 4 times 7, that's going to be 28. So I'm going to have 4 plus 28. That gives me 32 inside of my radical. All right, 32. Well, 32, are there any factors of 32 that are perfect squares? 32 is the product of 16 and 2, so I can reduce that radical into 4 root 2, and dividing each of the terms here in my numerator by 2, I get x is equal to 1 plus or minus 2 root 2. Now we end up with two solutions. The only reason here why I want the positive one is because think about the intersection points we're finding. We found this one here, and then also the intersection point down here. This would have been the negative one. Well, we want the one that has the positive x value. So that's going to be 1 plus 2 root 2. And so if that is our x-coordinate, we can find the corresponding y-coordinate by back substituting. Let's back substitute into this second equation. It would be y is equal to 2 times 1 plus 2 root 2 plus 3. Distributing through, we get 2 plus 4 root 2 plus 3, which gives us y is equal to 5 plus 4 root 2. So, not quite as nice, all right, but our final vertice here has the ordered pair 1 plus 2 root 2, comma 5 plus 4 root 2. There you have it, solving systems of inequalities.